The cart shown below, or over here, has a mass of 2m. The cart is released from rest and slides from the top of an inclined frictionless plane of height h. Express all algebraic answers in terms of given quantities and fundamental constants. So A asks us to determine the speed of the cart when it reaches the bottom of the incline. So we know from energy conservation that the kinetic energy after something falls a certain distance, its kinetic energy is going to be equal to its gravitational potential energy at the beginning. And this is because the gravity is a conservative force, and the energy does not get dissipated into heat or sound or anything else by friction or other methods of energy loss. So we're assuming that there is no other energy loss whatsoever to heat except for the transformation of the gravitational potential energy into kinetic energy as it accelerates down through the incline. So we know that the kinetic energy is given by 1/2 mv squared, and the gravitational potential energy is given by mgh, where h is the height off the ground. So this becomes 1/2 times 2m, since the cart has mass 2m, so you got to be careful, times v squared. That is equal to 2mgh. And if you notice, the two m's cancel out, so 1/2 v squared equals gh. And we need to determine the speed of the cart when it reaches the bottom. So the velocity as it reaches the bottom is going to be equal to the square root of 2gh. So this is the expression for the cart's speed at the bottom of the incline, and it is expressed in given quantities since it's using the height h and a fundamental constant, which is the gravitational acceleration. So for A, its speed at the bottom of the incline is equal to the square root of 2gh. 2 times the gravitational acceleration times the height h. Now B says, after sliding down the incline and across the frictionless horizontal surface, the cart collides with a bumper of negligible mass attached to an ideal spring, which has a spring constant k. Determine the distance xm, or the displacement of the mass. The spring is compressed before the cart and bumper come to a rest. So again, this is assuming that we have no energy losses throughout this entire process to heat or sound or any other form of energy. So again, our energy will be conserved, and all of that kinetic energy will be transferred into spring potential energy. So the potential energy that the spring has after being compressed is going to be equal to the kinetic energy it has after falling, which is the exact same thing as the gravitational potential energy it had. So just a quick reminder, the spring potential energy is given by 1/2 kx squared, where k is the spring constant and x is the displacement, or the distance the spring is compressed or stretched. So from that, we can say that 1/2 kx squared, and this x is the distance the spring is compressed, is equal to 1/2 mv squared. And again, this is 2m, not just m, since the mass says the cart has mass 2m, and v squared. You could also use the gravitational potential expression of 2mgh, and that would work too, but we don't really need that. We'll just use the kinetic energy here. So this, the two 1/2s cancel out, so get kx squared is equal to 2m times the velocity, which if we square it is simply 2gh. So the distance the spring is compressed squared is equal to 4 mgh divided by the spring constant k. So make some more room. Distance it is compressed equal to 4 mgh divided by k. So the distance that the spring is compressed, I'm going to write it over here. The distance that the spring is compressed is equal to the square root of this whole thing, the square root of 4 mgh divided by k. And of course you could simplify it further, but this will do for now. And again, it's given in terms of the constants that are given to us. So its mass, its height, and the spring constant k, and the fundamental constant, which is the gravitational acceleration here. And this is how you would solve this problem here.